We use the data that we just calculated for the solar power required. We also assumed that the hot temperature of the salt would be about 60 degrees Celsius above the hot temperature of the Rankine cycle due to inefficiencies in the heat exchanger, making the hot temperature of the salt 837 degrees Celsius. We also assumed that the cold temperature of the salt would be 285 degrees Celsius so that the salt would remain a liquid. The properties of nitrate salt were found on engineeringtoolbox.com. We found many different values for the solar heat flux up on the internet. They're ranging from about 250 watts per meter squared to 684 watts per meter squared. We found a fairly average solar heat flux to be 308 watts per meter squared, which we assumed to be the actual solar heat flux. Of course, the solar heat flux changes based on location and weather conditions, so the assumption is what we used. The reflectance of the heliostat was assumed to be 0.95, the albedo of bright aluminum foil. We also assumed that 80% of the space of the solar field was filled with heliostats. The other 20% would be blank space that workers could walk through. The aiming efficiency of 0.9 assumes that 0.9 or 90% of the heat transferred off of the mirrors makes it to the tower. The absorbance of a black body and the emissivity of a black body were assumed for the tower, so that it would be an ideal heat absorber. We also used the Stefan-Boltzmann constant, which can be found in many locations, and we assumed a tower area of about 10 meters squared, which would be the area of the box that is absorbing sunlight. We used these assumptions to calculate the area required to provide enough heat to the Rankine cycle. We first combined all of the efficiencies for a total efficiency of 0.684. This means that 68% of the sunlight going to the Mojave Desert surface was transferred to the solar power tower. We first assumed that there was no radiative heat loss from the tower. Using this, we calculated that the minimum and maximum area required to provide enough power were 2 square miles and 6 square miles. Although this is fairly large, it's not completely infeasible, assuming that cheap land was available. We then accounted for radiative heat loss using the Stefan-Boltzmann constant, the emissivity of a black body, the temperature, and the area that we assumed. This gave a heat loss of only 862 kilowatts, which is negligible compared to the heat required. Thus, radiative heat loss was negligible in this case. We then calculated the required flow rate of salt to provide enough heat to the Rankine cycle. We found that the flow rate of salt would be about 3,000 kilograms per second, or 3 meters cubed per second. This means that in order for the system to operate in the evening for 2 hours, the hot salt storage tank must be 2.3 times 10 to the 4th meters cubed in size, which is 26 times the size used in Solar 2. Thus, it would be a very large tank, but could be taken out across 26 tanks the size of Solar 2, which is not completely infeasible.
This is Joe Michelli again, and I'm going to talk about some other considerations for our concentrator solar plant, mainly the cost aspect. The capital costs of Solar 2 were around $39 million. Our plant is reasonably bigger, and our capital costs would be expected to be in the billions if any project was actually implemented. The operation and maintenance for Solar 2 was estimated to be around $9.5 million. Ours would also be a few factors larger. To help pay for our plant, there are many government incentives, including a Department of Energy grants and land acquirement that the government help with. We also have to look into the transmission of our power once it's actually produced, and the scale up. We also want to consider the weather conditions that our plant is at, including the day and night conditions. During the day, while the sun's actually shining, the plant will be producing more power than it does when there is no sun. The seasons also matter because it affects how long the days are and how hot and intense the sun is. And the location also matters. You obviously get more sun in the Mojave Desert than you do in somewhere that's really cloudy. To conclude, we compare diesel versus solar power. Diesel is more developed and has a smaller startup cost, but produces a lot of harmful emissions. Solar power is very expensive to start up, but once you do not need any fuel, and is also much cleaner and safer for the environment. Below are our references. Thank you for watching our video. We hope you enjoyed it.